Hello students, welcome back to your favorite channel Science with Mukherjeesir. Myself KK Mukherjee. Today we are going to discuss a very important thing, that is the activation energy. In the previous video where we have discussed the Arrhenius equation, in that equation I have told you that I have given some equation of the Arrhenius equation that can be represented by this form or not, that we have to see. These numericals I have given to you, most probably we have done it. Now we will solve it. Okay. Now you see, that is the first one. First one is this. Now we know Arrhenius, the basic equation is rate constant is equal to A e to the power EA by RT. Okay. K is the race constant, it is pre-exponential factor, and this is the exponent, that is EA by RT. Now, if we take the natural log on both the sides, what we will find? ln A is equal to it is ln K, ln A plus, and this will be, as it is the E base, natural log is basically, the base of the natural log is E. That is why it will be coming this. Mostly you understood it, right? So if it is this, now we can ln K minus ln A is equal to EA RT. Then we can write. Now, if we take this minus here, then what is going to happen? This will be ln A minus ln K, and it will be EA by RT. So, this equation will be ln A by K, that is EA by RT. Okay. So, this matches with this derivation. So, we can represent equation, Arrhenius equation, in this form also. Okay. Now we see the next form, that is D, derivation of this. Right? See, this is the form. The main form is this is the main form, and this form, whether we are able to convert it in that form, that we have to see. Now, if we take the derivation of this, first we have to take the ln, natural log of both the ends. So, in the similar way that we have done previously, ln this ln A equal to EA by RT. Now, if we take the derivation of ln K with respect to dt, when we derive with this is a constant. When we derivation of any constant is 0. So it is 0. Now you can see that is t have to be derived. So we can write it. Here is a minus value, and E A by R, and we derivate means we are derivating this by dt, and if we derivate this, it will come around, it will will be the derivation. You know what is when you derivate x to the power n, it will become n into x to the power n minus 1. X to the power n derivation is this. So you derivate it. So what we will find? We will find EA by R. We derivate it. This minus value will come here. Then it will coming around by 1 by t square. Okay. So you see, this is also matches EA by RT is. Okay. So this is again the right thing, right expression. Okay. Now we see this expression whether it is correct or not. Okay. For again we know ln k ln a minus e by rt. Now we are just converting this natural log into the log with base 10. That will be coming around this 2.03 is equal to 2.303 into log a Now we are dividing this 2.033 both the equation, both the side, left hand side and right hand side. So what we will get? Log k is equal to log a minus EA by RT into 2.303. So we can just rearrange this and we found log a is equal to log k plus EA by RT into 2.303. So this is also a right expression. The Arrhenius equation can be represented, can be like this question. We can do this, right? So, but this is not is possible. You can write it. This is not the correct thing. This is not a correct way of representation of the Arrhenius equation. So this is all. Now we will be going to discuss So in this video, we are going to discuss the activation energy that we know from the Arrhenius equation, that is EA is basically activation energy. What is that activation energy? Let us understand. Activation energy is basically when a reaction is underway, when the reaction is going on. There is it is been thought, it has been postulated that there is the collision between the reactant molecules. When the reactant molecule will collide with each other, it will form a intermediate, and this intermediate having the higher energy and highly unstable, and this is a basic complex form, and it will ultimately dissociate and give you the product. So what is the necessity for the conversion of the reactant to your product? That is the formation of this intermediate. As for example, I am telling the example. Suppose hydrogen plus iodine, it is giving you this HI molecule. Hydrogen molecule and iodine molecule react with each other, it will give you the HI molecule. So what is going here? Hydrogen and hydrogen molecule and iodine molecule both will collide with each other. Both will collide with each other and they will form a complex, intermediate complex. This is intermediate complex, and this intermediate complex is very much unstable, and this will break, dissociate, and it will produce hydrogen and hydrogen iodide molecules. The product. This is the reactant and this is the product. And between there is a intermediate complex. And this intermediate complex, if you plot it in the graph, this is the energy and this is the reaction coordinate. Reaction coordinate basically tells you the energy profile of the reactant molecule and the product molecule. And here you can see this is a reactant. The reactant having some energy, the molecules having some energy, and it will form an intermediate and it will form this product. So we can say this is reactant and this is product, and in between this is the complex, intermediate complex. We can write this. And this is A or activation energy. This is A or activation energy. So we can say that activation energy is basically the energy required to promote, to convert the reactant into the product. So we can write this. This is activation energy, the energy required to convert the reactant into the product, into the complex. Complex means intermediate complex. This is called the activation energy. Now question arises, how it gets the activation energy? What is the source of this activation energy? That is, you can easily understand, that is, when they collide with each other, there will be that energy. The molecule should have a sufficient amount of energy so that when they collide and they will form this intermediate complex, and this intermediate complex when dissociate and it will give a product, the product will naturally have a lesser energy. So at that time there will be liberation of the energy. Now think is that how this we can assure, how we can measure, how we can say this activity. When the reaction is going on, there will be millions of molecules, and all the molecules will not have the same level of energy. But it is not possible to monitor each and every individual molecules in respect of its energy. So what is there? Two scientists, Maxwell and Boltzmann. Two scientists, Maxwell and Boltzmann, highlighted this, and they are able to answer this question by statistical methods. What they show, they say it is true that we cannot able to monitor or we cannot able to say the X molecule will have that energy pattern like this way. We can't. Neither is required. They say you go for the proportion of the molecules which have a specific amount of energy. And in this way, they have given a distribution curve. This is called a distribution curve. In this distribution curve, the proportion of molecules in the y-axis. Proportion of molecules. Understand? Proportion of molecules, and here the energy. Energy basically when we are talking about the gas reactant, then that will be basically the kinetic energy. So in this point, suppose this amount of number of molecules is Ne. Ne is number of molecules. And total number is molecule is Nt is the total number of molecules, and N is the number of molecules having E energy. So in this point we can say Ne by Nt, the proportion of this molecule will have this amount of energy. Okay? In this fashion, you can see this is the peak of this distribution curve. This is the peak of this distribution curve, and you can see there is the highest, most probable. This is the most probable energy of the proportions. This proportion, if you calculate, if you see statistically, this will have the most probable, the molecule will have this amount of energy. Most proportion of the molecule. But this will have, here there is a lesser amount, lesser proportion, here is the lesser proportion. This point is lesser proportion, but this point of this curve having the most probable kinetic energy, most probable proportion of the kinetic energy. And now when the reaction is going on, you should have the sufficient energy, and that energy must be, it has been told, this energy. Suppose this is the activation energy, EA is activation energy, and above this energy the molecule will have this, above this energy, when they collide, and will give the intermediate complex, and the product will form. And naturally, this is EA is activation energy, and suppose this is one temperature is T, and now we increase the temperature. What is going to happen? The car you can say this peak is shifted, and this proportion of this value has been increased here. And when this proportion of this value, or the proportion of the molecule will have the activation energy, EA activation energy has increased, means there will be the rate of the reaction will be higher. And that is what we have observed when we increase the temperature. When we increase the temperature, basically what is going to happen? The proportion of the molecules will have the higher kinetic energy, EA and above become increased. And that is the reason with the higher increase, suppose this is T plus 10, the proportion is increased. You can see this proportion and this has been increased here. and this increased proportion will, the molecules will react and give you the lot of products, means the speed of the reaction will increase. Okay, so that is how we can visualize, we can understand how the activation energy is very, very important. And in that, the proportion of the molecules will have the higher energy than the activation energy will create the difference, and it will be higher when we increase the temperature. Higher temperature, that will be, proportion will be increased, and that is why this. And this proportion is defined by this. This is basically, you can see, this is the proportion of these molecules will have the higher kinetic energy. So we can say this is EA by I. And you can say that when temperature is increased, and this will increase. When temperature will increase, this will decrease. Means there will be the higher proportion of the. Okay, I think that is correct. That is, you can understood that how the activation energy going to influence the. So that is for this today's video. We will discuss later on the next part, that is how catalyst is going to influence the reaction, what is the role of the catalyst, that we will discuss, and also some numerical that may come, that also we will discuss. Okay, so all the best and be best.